On the homework.
We do 15.
15? Do you know what that is, or do I need to bust out the book? Got it? Anybody? Do you remember?
Number 4.
Number 4? Let's see. If I say what it is, we recognize it?
Yeah.
Does it ask you for like m of z plus h minus? Okay. So let me see if we can see what we got. So we have m of z equals x squared is what we're told. And z squared, sorry. And we want to find in number 15 fm of z plus h minus m of z. You know where this is heading, right? These are going to be our favorite problems, the f of x plus h minus f of x all over h. Just trying to build up to it. So this is our m function here. And in place of this z in there, we're going to plug in z plus h. So that means we're going to get the z plus h squared minus the whole m of z, which is going to be just the z squared. Now we're going to multiply this out. You remember our shortcut for this? I'm going to go OSU. First one squared, twice the product, plus second one squared. You okay with that? So the first one squared, twice the product, and then plus the second one squared, and then we still have that minus z squared. So everything that doesn't have an h in it should cancel, and it does. That z squared cancels with that minus z squared. Now we don't have the whole over h thing, which we will shortly. So we're not going to be able to cancel it, but that's going to be the end of that. For number 15. Okay. What else? Okay, well, we're going to talk then about logarithms. So this is 1.4. So this will be a little bit of a brief review. We did an entire chapter on this last year, but we're not going to go into that kind of detail. So the big key, the relationship, a logarithm base b of x equals y. So there is a logarithm equation, just a generic, in general logarithm equation. So there is a connection between logarithm equations and exponential equations. And so it's important to know that relationship, to know the connection. So to convert this logarithm equation into an exponential equation, do you remember what we do? Apparently not. So the base of the logarithm is the base of the exponential. And the logarithm is equal to the exponent, and that is our result. So we need to be able to go back and forth between the two. So if you have a logarithm equation, you should be able to convert it to its equivalent exponential equation and vice versa. Okay. In particular, there are some logarithms that you see a lot of, and so they are named specially. So a logarithm base 10, because our number system is base 10, is often used. And so it has been agreed upon that we don't have to bother to write the subscript 10 when it is base 10. And so that's known as a common logarithm. And you probably did quite a bit of that in Algebra 2 and some of it in AP Prep as well. Now, there's another one, which I think when you're beginning, up until you will see the importance of it this year, prior to that, you're like, why do we make such a big deal of this Euler's number E? But a logarithm base, this funny Euler's number E, also gets a special name, and it's called ln x, or natural log of x. So that is called natural log, or natural logarithm of x. Okay, and I think the n here comes from the natural log there. So we will see eventually, once we start learning more calculus, there's a reason this is so important. And we'll find out that finding its derivative, whatever that is way easier than it is with any other logarithm of any other base. So given the choice, we will pick a logarithm base e. And then because of that, we're going to go with its inverse, the exponential base e as well. And we'll say we'll see that its derivative and integral will be like favorites of ours because they're so easy to do. Whereas if we don't have a base Euler's number, it's kind of a pain. It gets kind of annoying. So for that reason, in calculus and higher math, you almost exclusively see natural logarithms and exponentials base Euler's number. So we have then this relationship that these are inverses of each other. So y equals e to the x with your finger in the air. Can you show me what that graph looks like? Oh, very good. It's a classic exponential growth because Euler's number e is, approximately 2.71, whatever. But it's bigger than 1. And so it's going to be exponential growth. And then its inverse, y equals natural log of x. Can you show me what that looks like? Oh, very good. You're anticipating my question even. Yes, so it's going to look something like that. And so in particular, you can see as happens with inverses, this point that is the y-intercept for the exponential 0, 1, the corresponding point is that x-intercept 1, 0. And that is, these are reflections, as are all inverse functions in the line y equals x. And we can also talk about like domain and range. So the domain of the exponential e to the x, the x values are what? That was a question. Is what? All real numbers, yeah. We use all of them. And its range is going to be, y strictly greater than 0. And then you can see from the graph, but you also know that the relationship between functions and their inverses is the domain of a function is the same as the range of its inverse and vice versa. So the domain for the natural logarithm is going to be
Y greater than 0?
We'll switch it to x though. Yeah, so the x greater than 0, yeah. And the range is going to be all real numbers, as it will with all logarithms. Okay, so let's look at some what we call properties of logarithms. These are going to be important for us as well. So refreshing our memory, properties of logs that we talked about a lot last year. So one is, and I'm going to use natural logarithm here, but it's logarithm any base. So this works for all logarithms. So the natural log of x times y, we can break apart, or we say expand into what?
Natural log of x plus natural log of y.
Yeah, exactly. So we say the log of a product is the sum of the logs. And we sometimes go the other way around. So we call going from left to right expansion, and going from right to left condensing that into a single logarithm. So the natural log of x divided by y is going to be, this is going to be a subtraction, natural log x minus natural log y. And again, we go right to left or left to right either way. And then one you use a lot when you're solving equations, exponential equations, is natural log of x raised to the n power. We can do what? Yeah, bring the n out in front as a multiplication. Very good. Okay, so there's some inverse properties that are kind of funky, but we need to know and make use of. This actually comes up quite a bit. Logarithms, natural logarithms and exponentials base e are just a foundational piece of calculus. So because we know that an exponential base e and a logarithm base e, a natural logarithm, are inverses of each other, then taking the natural log of e to the x is like saying f inverse of f of x, and so that would have to be equal to x. Right? They cancel each other out. They undo each other. And similarly, it may look kind of weird until you get used to it, but e raised to the natural log of x will also be x, because they will cancel each other out. It's like saying f of f inverse of x. So this is true about now natural log of 1, but logarithm any base of 1, can you see that, is going to be 1. So imagine now you're going to say, remember you got your base e here. E to what power is 1? 0, right? Anything to the 0 power is 1. So a logarithm of any base of 1 is going to be 0. And then you get things like, so let's see if we can use these inverse properties. The natural log of 1 over e to the third. We think about how to simplify this. So 1 over e to the third, we could write just as e to what power? Negative 3, right? So that's going to be the natural log of e to the negative 3. So negative exponents become fractions. Remember, fractional exponents become radicals. Okay, now we're in this place that we were before. So the natural log of e to the negative 3 is going to be negative 3. See it? Okay, now let's do natural log of, say, the square root of e. Now, square root of e is e to what power? There's the fraction, right? So radicals give you fractional exponents. Fractions give you negative exponents. So that's natural log of e to the 1/2, which then must be 1/2. Okay? So let's solve some equations, and we're going to have to bust out our calculators. And we'll talk about some different strategies here that might be AP exam friendly. So let's solve these. These are going to require us to use logarithms. So 3 to the x plus 5 is equal to 13. So what is our strategy going to be here? So what we see is that the variable is in the exponent. Okay, so what is that going to suggest to us? We have to use logarithms along the way. So we want to isolate the exponential first. So I'm going to move the 5 to the other side. And so we're looking at 3 to the x equals 8. Now, we have two buttons that appear on the front, a common logarithm and a natural logarithm. Just to get more familiarity, I'm going to say let's use the natural log. It doesn't really matter. And I think you can even get to a menu that will get you a logarithm base 3 on some of the newer calculators. But I'm going to just take the natural log of both sides so that we get hopefully a little bit of a comfort level with this thing. Now, what happens to the natural log of 3 to the x? The x comes in front, so you get x natural log 3 is natural log 8. And now we can just divide that natural log 3. It's a funny number, but it's just multiplying the x. And so we're going to get natural log 8 over natural log 3. Is that okay? So throw it on your calculator. And we're going to round to 3 decimal places. Reese, did you get it already?
Yeah. I got 1.893.
I think that's right. I think 1.893. Is anybody not getting 1.893? We're good to go. So this, I think on this particular problem, if this was an AP exam question, which it wouldn't be, that's not really in that style, I would still do it this way. But I just want to point out another way of doing it because this is another calculator skill that's a must-have. So we could, now theoretically, you could call this left side y1 and this right side y2, graph those on your calculator and find the point of intersection. I think when I do something, if I'm going to use that strategy on an AP question, instead of doing it that way, I would suggest making it equal to 0. So I would subtract the 13 over and make it 3 to the x minus 8 equals 0. And now put that in as y1 and find the 0 rather than finding the point of intersection. And the only reason I would say that is because sometimes when you graph, these it's not a big deal because we know it's going to be not too far away. But sometimes this can be a number that might be really big or really small. It might be something like 235 or negative 57. And if you start doing this on an AP exam, which is going to be a time-pressured test, and you start with a 10 by 10 window and you can't see anything. So then you got to start guessing and say, well, let me change the x min and x max, y min and y max. And in the first place, it's taking time. In the second place, it's stressful because you're like, oh my God, do these intersect? Or where is it? I can't find it. Whereas if you make it equal to 0, at least you have taken part of the uncertainty out of it. Because you don't have to worry about the y min, y max. You can go like negative 1 to 1 or negative 2 to 2. Now you just got to play with the x min and x max to see where does it cross the x-axis. And then you're going to find the 0 rather than the option that says find the intersection. You understand what I'm saying? Do it that way. So let's put it in there as y1, and you can choose your y min and y max, right? Just to be negative 2 to 2 or something like that. And it doesn't really matter what you have your x min and x max. You know it's going to be somewhere in the neighborhood of 2. So negative 10 to 10 is fine, or you could change it up a little bit. But that's finding the 0 and finding a point of intersection are skills that they tell you on the AP calculus syllabus that you must have. So you have to be able to do it this way. Not that this particular problem would require you to do that. Okay. Did anybody not get 1.893 that way? I need nods of heads. Yes, I got it. No, I didn't. I need to get some kind of response here. Okay, so the population of Burkina Faso in millions is given by this equation. This formula, P of t is equal to 12.853 times 1.03, that's a 4 raised to the t power, with t equals 0 in the year 2003. So my question to you, well, first let's just refresh our skills from all that stuff we did last year. So what is the population in 2003? When you look at this, can you tell, like in a second, what the population is in 2003? Say it out loud if you do. So I don't want to know yes or no. I want to know, what is it? Yeah, it's going to be 12.853 million, right? Because at t equals 0, anything to 0 is 1. So remember, this is the initial value. This is the value of this, whatever that is, at time 0. And so do you remember what is what's the growth rate? By what percentage is this population of Burkina Faso increasing or decreasing?
3.4.
Good. So remember, this is the 1 plus r. So if you subtract off the 1, the 0.034 is, if you make it into a percent, is a growth of 3.4%. Okay, so your challenge is, when will the population reach 20 million? When will the population reach 20 million? Okay. Anybody need help getting started? You can consult and collaborate, so feel free to actually talk to your neighbor.
Three decimals?
Yeah, always 3 decimal places, yes. What'd you get, Sam?
I got it wrong.
Oh,
I got T is 13.224, so the year was in 2016.
so in 2016 sometime. Did you get that too, Grafton? Okay. Anybody not getting this? Okay, cool. All right, so let me give you a little bit different one here. So carbon monoxide near a busy road. So carbon monoxide near a busy road. Decreases exponentially. Decreases exponentially at a continuous rate of 3.3% per meter. Kind of funny units there. But the idea is, you got some really busy road, think like, something in the middle of LA or downtown Denver or something like that. And so with all the traffic going through here, there's a lot of carbon monoxide in the air. So as you walk away from that, the further away you get, the less that kind of carbon monoxide cloud or whatever that you experience. So the carbon monoxide levels decrease as you move away from that. Does that kind of make sense? Okay, so what your question, your challenge is, can you find at what distance is the CO level? So that's supposed to represent think like a chemist, 1 carbon, 1 oxygen. I'm not talking Colorado here. So that's what distance is the carbon monoxide level, half of what it is at the street. Okay. Should we talk about how to do this? Or do you know? Talk about? Okay, so we need some kind of an equation here, an exponential equation for this. So it's decreasing exponentially. Now it talks about a continuous rate. So we made a big deal of this last year. The authors of our textbook say, when they say continuous rate, what is that telling us? What's the base of our exponential? e. Right? Continuous means it's going to be a base of the exponential is Euler's number e. So I'm going to pause a minute here. When you're in Algebra 2 and even in pre-calculus, you learn a bunch of different formulas for exponentials that have different application. Sometimes you learn, this is the exponential you use for half-life. This is one you use for doubling time. This is one you use for continuous interest. This is what you use for simple interest, and so on. Well, we're going to have so many things we have to memorize in AP Calc. I want to declutter that. So in AP Calculus, every exponential question you will ever be asked can be answered with just a basic, and we would choose base Euler's number. So you can do it, so I would say just remember, and most people can remember 8 hertz, or that PE to the RT that you learned for continuous interest. That will serve you well for any kind of exponential problem that you'll be asked on an AP exam question. So the only thing that couldn't do is if you had something like compound interest, where you have A is P times 1 plus R over N to the NT. But that isn't on the AP syllabus, so you won't see anything like that on an AP exam. Okay, so this will work for anything. Now, usually in math, you might write something more like y equals something like, say, A e to the kt or kx or something, maybe kx. It doesn't matter what you call these letters here, P, R, A, K, whatever. It's all the same. I mean, it's just a way that you can remember it. The big thing is you have to remember how to get started. So we okay with just using PERT? Okay, so if we're going to use this, then what do we know? So because it's a continuous rate, that means we're going to choose E as the base. What is this 3.3? It's a decreasing by 3.3%. So what is that telling us?
The R is negative 0.03.
Exactly. So we're going to say A is this PE to the negative 0.033. And we can use T, or in the context of this problem, I don't know if that matters to you or not, but it's not really time, right? So our carbon monoxide level is changing with a distance, right? How many meters from the road? So is it okay if I just call that D to suggest distance there? Okay. Now what? When will we have half as much? Well, how much do we have at a distance of 0? If D is 0, we're right on the edge of the street, in the middle of the street there. How much carbon monoxide are we breathing in? P. I don't know what that is, but it's P in this equation. You see that? So you put in 0 here, each of the zeros is 1, it's going to give you P. So how much is half of that going to be? 0.5 P, or 1/2 P. Is that okay? So I'm going to replace this to answer our question. When, or not when, what distance, how far away from that road do we have to be to get half as much carbon monoxide? We're going to solve this for D. So it turns out it doesn't matter how much you have here, because it's going to divide out, right? So now we have a half is equal to e to the negative 0.033D. All right, to there. And now what? Natural log both sides. Oh, now it gets fun. So we have natural log of half equals natural log e to the negative 0.033D. Oh, now you don't have to, because we're going to go to the calculator shortly, but we just talked about these properties of logarithms. What a great opportunity to reinforce what we just learned. The log of a fraction we know is natural log of the numerator minus the natural log of the denominator, right? Log x over y is log x minus log y. And we said that the natural log of an exponential base c, these are inverses of each other. On this side, we're going to get negative 0.033D. Okay? It gets even more. We said the natural log of 1 is We said 0, very good. So we get negative natural log 2, negative 0.033d. So d is going to be negative natural log 2 over negative 0.033. And you can throw that on your calculator.
21.004.
Good. I think he did that in his head. So it's going to be about 21, and what's our unit on that?
Meters.
Excellent. Excellent, excellent. Okay. 21.004 meters. Anybody not getting that? I'm going to give you a moment. See some of you still punching in that result. Okay. So I'm not going to get through everything here. So this is one of those cases where you need to watch that video in the support materials and kind of see the end. I want to talk a little bit about a really, really tough problem we talked about last year, but it's been a while. And my observation is some of you have pretty much wiped the slate clean and forgotten everything we ever talked about last year. I'm just kidding, I hope. So let's talk about solving something like 10 to the x plus 3 is equal to 5 e to the 7 minus x. So I want to talk strategy first, and then we'll get into that and actually work it. So notice, first of all, we're solving for x, and you see that x is in the exponent. The variable's in the exponent, which means we're going to have to, at some point in time, take a logarithm. Now, what's worse is we have a base 10 here and a base Euler's number there. So we have two exponentials, and they're not the same base. That just adds a whole another layer of difficulty to this. Now, should this appear on, say, an AP question, which it never would, this is not that kind, it's just not an AP style question. But if you were under time pressure, to get an answer to this, you're going to have to be able to use your calculator. So if a calculator is an option, what is the most efficient way of proceeding here? Anybody with an idea?
Use the graphs.
Graphs, exactly. So you could call the left side y1 and the right side y2. Graph those. Now you may have to play with the window a little bit to see where that intersection is going to be. And then you're going to have to use the calculate intersection. So second trace, go to the calculate menu and do that. Questions?
One thing, if you hit zoom and hit 0, it should fit it. It doesn't always work, but
Okay.
sometimes it does.
I didn't know that. So there's a thought. Okay, but remember, you got to see a place where the graphs intersect before you can go on. Know what we're doing? You got it already, Reese? Oh, you're just waiting for the starting gun. Okay, give it a shot. Pretty big window of the Y's, isn't it?
Mm-hmm.
So this is a case too where an alternative is you could subtract 1 to the other side. Just putting that out as a suggestion. Because if now you're looking for where is it equal to 0. And so now you can choose your y min and y max just to be like -1 and +1. You're just going to look for where does it cross the x-axis. It takes away that guessing of how high up do you have to go. Does that make sense? It might make your life a little bit easier. And I think you don't have to have a very, very big window on the x-min, x-max. If anybody finds it, let me know, and we'll see if we're on the right track. So I think I got the answer. Libby, did you get it?
Not yet.
Not yet.
I think I might have got
What's that?
I think I might have got it.
What'd you get?
2.604.
I think so. Is anybody else getting that? Unless I got it
Or
wrong.
2.605.
I had an answer, but it's ridiculous.
It's ridiculous, huh?
Yeah.
But the y-max is 500. Gee, okay, do that.
I got 0.
I don't know if I can get mine on the camera is the only thing, but I'm afraid I'll just do it anyway. So if I interrupt the video, I'm just talking to them for people at home. So if I lose the video here, then you'll just have to figure it out on your calculator. But I'm gonna switch over to my calculator here and see if we can find it. My answer that I wrote down may not be right. So, too much technology. Okay, I think now I can go to my calculator.
0.515.
That's what, did you get that? That's the answer I have. So I have 0.515. So I'm going to try 10 raised to the x plus 3, whoops, plus 3, and then minus the 5e to the 7 minus x. If we agree, then I have a lot more confidence. So I'm going to choose a window, and I'm just going to go, like -2 to 2, because I'm playing on that fact that I think it's 0.515. And I'm just going to go -1 to 1. This is the real advantage, is you choose your x min and x max and be okay with that. So now I'm just looking for where it crosses the x-axis this way. Now let's play with oh, there we have it. So this is looking good. I'm going to now calculate the 0, so second 0. Now, so I'm way over here at 0. I'm going to move I'm using my right arrow. I'm watching those y values because I want to keep the answer negative because this is rising from left to right. And there I go, whoa, come back here. So let me go back to negative. Now, my next click is going to make it positive. So I'm going to hit enter. That's the left bound. Now when I go right click, I'm at a pretty big positive. That's a right bound. I'm going to hit enter. And then I don't need a guess, so I'm just going to hit enter there. And it does the heavy lifting. There it is, 0.515. Very nice. Is that okay?
No, I'm confused.
Okay. Did you have your graph?
Yeah.
Let me take a look. So go back to let's go by each row. So you just see that. So you have 10 to the x plus 3 is good. 5e to the 7 times that looks good. Okay. But hit the window there. So you had -10 to 10 is fine. You get y in. Your y max is got to be way bigger now. You see 500. So now you're.
You did the 2 equations, right?
Yeah. She did 2. It's not looking the way it should be. Y equals again. Plus 3. 7 minus x. Why is that not looking the way we want it to? Go back to window. Let's try going minus. Let's go -2 to 2. Try to declutter things a little bit. Let's go just -1 to 500. Oops, sorry, 500. And then let's drop down and make the y scale 100 so we don't have such a. There's it. Don't show high enough. Let's go Windows, go files for 1 day. Still don't think we have enough on the screen. Let's be bold.
This is why I think the zero looks better. Honestly, I think the zero snap. Still not high. See what I mean? Okay. So let's go. Do you have a minute? Or do you have to-
No, I can.
Okay, so let's try 10,000 for the one.
Yeah.
Here's our first one, 10 to that power. I think we're going to get it here. Here's our next one. There. Now let's see if we can calculate the zero. I think this is going to work because that looks like it's about 0.5 because we're only going to 2 on the x. The first curve you can just hit enter. It's just,
Oh.
so yeah, second curve is okay. Now guess you do that. So you guess you move the cursor. There we go. So the problem, see, and that's why I think sometimes, you know, if you're trying to do all the stuff we were doing there on a timed test, then you're starting to freak out because you're like, the time. Whereas this kind of narrows the search down because you know it's going to be on the x-axis. Now you're just playing with your x-min and x-max to make sure you see it cross.
Here you go. Do you want me to put it over
Yeah, I'll
there?
wipe it off there, thanks.
Yeah.
Can you get the stairs this time of day, kiddo, or is that?
No.
No. You're alert?
Yeah.
Okay.